Alright, today we're talking about section 2.6. And in this section we're talking about other types of equations. So we'll be looking at various types of equations that we can solve. The first type that we're looking at is involving rational exponents. So let's remember our definition of rational exponents and what those actually means. So remember, a rational number is a number that can be written as a ratio of two integers. We also usually refer to them as fractions. So an example, we could have a raised to the m over n power. And there's various ways we can write this, but for you to understand, I hope you can see that any fraction m over n, I could write that as m over 1 times 1 over n if I needed to. Okay. Which would be the same thing as m times 1 over n. I could also commute these. I could write that as 1 over n times m. Okay. So both of these things can happen. And why that's important to us when we're dealing with exponents is that we could either take our base, a, this is our base, and first raise it to the 1 over n power, and then raise that to the m power. Or we have the option of first taking our base, raising it to the m power, and then raising that to the 1 over n power. Something we should also probably remember is about nth roots. So if we are taking whatever root, say n, so if n is 3, we'd be taking the cube root. This is written in radical form, but we could write it as a rational exponent as 1 over n. So how that helps with our rational exponents is sometimes it's going to be easier to deal with the rational exponent, and sometimes it'll be easier to deal with the root. So for example, our first one, a to the 1 over n, whatever root we're taking, and then we could raise it to the m power. This means that I could take the square root, not the square root, the nth root first, and then raise it to the power. Or we can do it the other way. I may want to first raise the base to the power m, and then take the root. So in that case, how should we look at this? Well, then we'll take a to the m power first, and then take the root. We should know two common roots by heart, their graphs. Okay. So the first one we should know by heart is the square root. Okay. The square root of x, our basic parent function, looks like so. So this is y is equal to the square root of x. This is the point 0, 0. This is the point 1, 1. If you take the square root of 4, you get 2. If you take the square root of 9, you get 3, etc., etc., etc. So the domain of this graph is not all real numbers. The very first number of x that we can pick up is 0, and we include 0 because the square root of 0 is 0. And then it will continue on towards infinity. We continue to take square roots of positive numbers. When we take the square root of a negative number, it's an imaginary number, and we do not graph in the imaginary numbers in the xy plane. Therefore, that's why we restrict these numbers. Another graph we should know is the cube root. Its graph looks like this. Again, we have the positive arch, but we'll also get the negative arch. This is a sketch of y is equal to the cube root of x, which is the same thing as x to the 1/3 power. Again, 0, 0 is on the graph. The cube root of 1 is 1. The cube root of 8 is 2. The cube root of 27 is 3. These would be on there. However, it is also possible for us to take cube roots of negative numbers. So, for example, from here, if we want the cube root of negative 1, well, we're looking for groups of 3, and I could rewrite negative 1 as negative 1 times negative 1 times negative 1. And there is a grouping of 3 negative 1s, so the cube root of negative 1 must be negative 1. Also, for example, we could take, we have the point negative 8, negative 2, because if we put negative 8 into the cube root function, I could rewrite this as negative 2 times negative 2 times negative 2. Now there's a group of 3 negative 2's, so the cube root of negative 8 is negative 2. Hence, we have that point. Okay. The difference here now in domain is that we are no longer restricted, but the domain will be all real numbers, or go from negative infinity to positive infinity. And the difference of these two graphs comes down to the multiplication. Because of the negatives and negatives make positives, and then positives and negatives make negatives, it is possible with cube roots to get a domain of all real numbers, but with the square root we cannot. For example, we can't take the square root of negative 4, because if I was to write this out, I would need a negative 2 and a positive 2, and these are not the same number. Okay, so there is no grouping. And that is one of the reasons for the domain restriction. Okay, let's put all this together and try and solve radical equations then. Well, actually, first let's simplify some rational exponents. All right, so if, for example, we had 8 to the 2/3 power, what we're saying here then is 8 is the base, 3 is the denominator, and so that is the root. And I know the cube root of 8 is 2, so I'm going to choose to take that cube root before I then square it. So this becomes, well, the cube root of 8 is 2, and then we square that, which is 4. We can still have negatives with the rational exponents. That's no problem. So if we had 8 to the negative 2/3, remember I'd think about this as over 1. And if I want to make this exponent positive, I can just push it through the denominator. It would leave me with 1 up top, and now 8 to the positive 2/3. But from above, we saw that 8 to the 2/3 power is 4. We could also do, let's try one more. We could also do 64 to the negative 1/3 power. Again, I want to make this exponent positive, so I'm going to push it through. That will leave a 1 in the numerator, and now it's 64 to the positive 1/3 power. And if we convert this to a radical, then I'm taking the cube root of 64. Since I'm taking the cube root, I want to look for groups of 3, so let's take the prime factorization of 64. 2 goes into 64 into 6 3 times, and 2 goes into 4 2 times. 2 goes into 3 1 time with a remainder of 1. So then 2 goes into 12 6 times. 2 goes into 16 8 times. 2 goes in 4 and 2 and 2. Now I'm looking for groups of 3 because this is the cube root. Okay? And I have one group of 3 there. Okay? So that can come outside of the radical. So from that group I get a 2. And here's another group of 3. So I will multiply these together. And so in the end, this is also equal to 1/4. So that's how you simplify rational exponents. Now let's solve with some rational exponents. So for example, if we have x to the 5/4 power is equal to 32, I want to remember what root I'm taking. Okay? So if I rewrite this, this is x to the 5th, the 4th root of that, will be equal to 32. Now the way I can solve this is I want to get to x. Okay? So to get to x, right now it's underneath this 4th root. But the way I can undo the 4th root is that I can raise it to the 4th power. Just like, for example, if we were solving the square root of x is equal to 2, what I could do is I could square it on both sides to get x is equal to 4. Okay? So that's what I'm going to do here. And the 4th root and the 4 will cancel and leaving just x to the 5th. Now here, I don't want to raise 32 to the 4th power. I do, that's what it says, but I don't want to multiply it out. So let's simplify this. We know 32, taking the prime factorization, 2 goes into 3 one time with a remainder of 1, then 2 goes into 12 6 times. 2 goes into 16, 8, 2 goes in 4, and 2 and 2. So what that means then is that 32 is 2 to the 1, 2, 3, 4, 5, 2 to the 5th power. So our equation is looking like x to the 5th is now 2 to the, remember if you're multiplying, if you're going power to power, you multiply these exponents. So x to the 5th is equal to 2 to the 20th. But my goal is still to get to x. And right now x is being raised to the 5th power. So I need to take the 5th root of x on both sides to do it. Like, for example, when x is cubed is equal to 8, let's say, what I need to do then to undo the cubing is I need to take the cube root of both sides. So then in this case, the cube root undoes the cubing, so x would be equal to the cube root of 8, which is 2. So here I'm dealing with a 5th power. I'm going to take the 5th root. So that will cancel out, and I'll be left with x. And now I need to think about how to simplify this. So I'm really looking for the 5th root. So now I'm going to be looking for groups of 5. Okay. Well, 2 to the 20th is when I'm multiplying with like bases, I could add the exponents. So 2 to the 20th is 2 to the 5th times 2 to the 5th gets us to 10, times 2 to the 5th gets us to 15, times 2 to the 5th gets us to 20. So now I know that here is one group of 5 2's. Okay. So I can pull a single one of those out. Here's another group of 5, so I can pull that 2 out and multiply by it. There's a group of 5, I can pull that out and multiply by it. And lastly, there's a group of 5 here. So our solution must be that x is equal to 2 times 2, which is 4, times 2 is 8, and times 2 is 16. So the value that solves this is x to the 6, is x equal to 16. So let's do our check. We say 16, I'm putting it back in here, to the 5/4 power. And we're going to ask ourselves, does that equal 32? Okay. Well, simplifying the root, this becomes the 4th root from here, and then I'm going to raise that to the 5th power. Well, the 4th root of 16 is 2 from here. Okay. So this is 2. And then 2 to the 5th is indeed 32. So this checks. Let's try another example. Let's try x to the 3 halves is equal to 125. So again, let's write this out in radical form so we know exactly what we need to do to this. Okay? This means I'll be taking the square root of x, the square root of x, and let's put our cubed underneath. Okay, from here is equal to 125. So if I want to undo the square root, I'm going to square both sides. And on this side we will have simply x cubed is equal to, again, where I don't want to square 125, so let's reduce it if we can. So 125, 5 goes in there, 5 goes into 12 2 times with a remainder of 2. Then 5 goes into 25 5 times. And then 5 goes in 5 times. So that is 125 is 5 cubed. Now let's simplify, cubed. Let's simplify our exponents over here, and going power to power, we actually multiply the exponents. So the base is 5, and 2 times 3 is 6. So x cubed is equal to 5 to the 6th. To undo the cubing, I'm going to take the cube root. So we'll get x is equal to the cube root of 5 to the 6th. But let's look at what that means. The cube root then, I know 6 is a multiple of 3, so I could write this as 5 cubed times 5 cubed. Right? When multiplying with like bases, you add the exponents to get 6. Now here's one group of 3, so that will come out. And here's another group of 3 for the cube root, so that will come out. And in the end, x must be equal to 25. We could also see this from here, where we could rewrite this in radical form. So the root here is 3. Okay, so that becomes the denominator. Okay. The power is 6. And now this will simplify. 6 over 3 is simply 5 squared, which is equal to 25. So there's a couple of ways for you to do it. Let's try a different problem. Now, for example, let's do the quantity x plus 5 to the 3 halves power is equal to 8. I'll want to rewrite this in radical form so I know what I'm looking at. And so I'm taking the square root. So we want to take the square root of the quantity x plus 5, and we'll leave the cubing there. And that is equal to 8. Now to undo the square root, we'll square both sides. So the squaring will undo the square root, and we'll have the quantity x plus 5 cubed is equal to, well, 8 and 8 is 64. I'm still trying to get to x. X is being cubed right now, so I need to take the cube root. The cube root and the cube will undo each other, so on this side we'll have x plus 5 is equal to, I think we did this one before, I think it's 4. 2 goes in 32, 2 goes in 16, 2 goes in 8, 2, 4, 2, and 2. So there's one group of 2's, another group of 2's. So the cube root of 64 is 4. And then we can solve for x by subtracting on both sides. X must be equal to negative 1. Okay, so there is one thing we need to be careful about. Let's try this. What if it had been x plus 5 to the 2/3 power equals 8? Let's see how different this would be. Okay. So now when I write it in radical form, I'm taking the cube root of x plus 5. That quantity is squared, and that equals 8. Now to undo the cube root, I'll cube both sides. The cube root will undo this, and we'll be left with x plus 5. That quantity squared is equal to, and again, just simplifying and using radical, or exponents, 8 is 2 cubed. So this is x plus 5 squared is equal to 2 to the 9th. 3 times 3 is 9. Now to get to the variable here, I'm going to have to take the square root. And here's where we have to be careful. Let me simplify this, just because it's, well, let's find out what 2 to the 9th is. So 2 to the 6th is 64 times 8. 2 cubed is 8. It's 32, 48, 49, 50, 51. Okay, so the square root of 512, which we could certainly simplify, but for this, we will hold on. Remember, when we're solving, if we have x squared is equal to 9, once we take the square root, we get x is equal to, now remember the plus or minus, the square root of 9. Okay. This is because it's an even root. Okay. And the same thing will happen here. I'm taking the square root, so the answer needs to be plus or minus the square root of 512. So don't forget the plus or minus when you're taking a root that is even. Okay. And then I can just subtract 5 from both sides. And so our answer would be negative 5 plus or minus the square root of 512, which is 2 separate answers. It's negative 5 plus the square root of 512, or negative 5 minus the square root of 512. So just be careful with that, and taking with even roots, you need to put a plus or minus. So that's one type of equation that we have. We also have equations that we could solve by factoring. So for example, if we had 5x to the 4th was equal to 80x squared, our temptation here might be to divide out some x squares. However, the problem with that is that we don't know what value x could be. So never divide by a variable because you could be dividing by 0, and dividing by 0 is undefined. So instead, factor. And how will we do that? Well, let's move everything to one side so it could be factored. Now from here, I can see that there's a greatest common factor of 5, and then also an x squared can come out of both. So once I factor that out, then the first term here I'm left with x squared, and then minus 5 goes into 80 one time, and 5 goes into 36 times. Equals 0. Now that it's factored, what we can see then is I have two things being multiplied together, so either the first thing is equal to 0 or the second thing is equal to 0, our second factor. From here I can divide by 5 to get x squared is equal to 0. Then take the square root. Square root will undo the square, so we're left with x is equal to plus or minus the square root of 0. Well, the square root of 0 is just 0. And 0 is neither positive nor negative, so we just simply say x is equal to 0. On this side, we'll get x squared is equal to 16, moving the 16 over. Now we take the square root, and we have that x is equal to plus or minus, don't forget that, the square root of 16 is 4. So in this case, we have 3 different answers. These are the values of x that make the function 0. So, for example, if we were to sketch a graph of this, it will actually look something like this. And it turns out the x-intercepts for this graph, this one's 4, 0. This one's 0, 0. This one's negative 4, 0. And that's not by coincidence. Notice that when x was 0, we set the function equal to 0. So if x is 0, y is 0 here. When x is positive 4, the function was also 0. So here we have the x-intercepts that come to the graph. So one way that you can solve a function equaling 0 is to look for the x-intercepts, and the x-coordinates of the x-intercepts are your solutions. Let's try another one. Here we have 12x to the 4th is equal to 3x squared. Again, we do not want to divide by a variable because we could be dividing through by 0. So let's factor instead. And to do that, we need to move it over everything to one side. So we have 12x to the 4th minus 3x squared equals 0. We look for a greatest common factor, and that's a 3 between the 12 and the 3. I can pull that out, and I have the x squared. Leaving behind 4x squared minus 1. Okay, be careful about that, because when you redistribute this through, you need that 3x squared there, equals 0. Now it's factored, so we can use the zero product property, and so either the first thing is equal to 0, or the second thing is equal to 0. Solving this, dividing by 3, we have x squared is equal to 0, taking the square root, so x must be equal to plus or minus 0, which is just 0. Over here, we'll add 1 to both sides, and then we can divide through by 4. Now we can take the square root. So x is equal to plus or minus the square root of 1/4. And using the property of radicals, well, that's plus or minus the square root of 1 over the square root of 4, which is plus or minus the square root of 1 is 1, the square root of 4 is 2. So plus or minus 1/2. Let's do one that can be factored, but it's factoring and we're using rational exponents. So, for example, let's say we have 3x to the 3/4 is equal to x to the 1/2. Again, we do not want to divide by a variable, so let's move everything to one side so we can factor. So 3x to the 3/4 minus x to the 1/2 is equal to 0. Let's pick the smaller of the two exponents. I have an x to the 1/2 in both of these, so I'm going to factor that out. So x to the 1/2 comes out. Now we have to be careful about what's left behind. All right. So what we're doing here, factoring out, is the same thing as dividing. So in our second term, x to the 1/2 over x to the 1/2, well, that's just the number 1. Equals 0. Here, the 3 will stay, and remember that when I'm dividing with like bases, we have to subtract the exponents. So this is x to the 1/2 times 3x to the 1/4 power. 3/4 minus 2/4 is 1/4. Minus 1 equals 0. Now this is factored, so we can again split it up. It's either that x to the 1/2 equals 0, or 3x to the 1/4 minus 1 equals 0. And now we can solve. To solve this one, I simply need to square. Because 1/2 times 2 over 1 is x to the first power. And 0 squared is 0. Here we have 3x to the 1/4 is equal to 1 if I add 1 to both sides. Now let's divide by 3. So we have x to the 1/4 is equal to 1/3. And perhaps I should have done this over here and written it in radical form, so let's do that now. This is the 4th root of x is equal to 1/3. So if I want to undo the 4th root, I need to raise to the 4th power. Now the 4th root of x raised to the 4th power will undo itself, and we'll get x is equal to 1/3 to the 4th power. Remembering our rules of exponents, though, that's the same thing as the numerator raised to the 4th power and the denominator raised to the 4th power. 1 to the 4th is simply 1. 3 to the 4th is 9 times 9, which is 81. So in this case, we had 2 solutions.